Sport is an area where movement is really central and where very subtle aspects of movement can make a huge difference in performance. And a lot of these subtleties can be missed with the naked eye.
And when we see this hidden information, we can infer a lot more information from that. Say, is the player doing well? What severe the injury is in the player? Or was the movement correct or not correct?
So one of our goals is to provide the same kind of thing that slow motion has been providing for sports. It's to help both the fans, the trainers, and the players see more things and better appreciate what's going on just for entertainment purposes, to just be more in the action and really realize what's happening, or for training and improvement reasons, see that maybe this muscle is not doing quite the job it should be doing. Or in the case of injury, see that maybe this muscle is being strained a little too far and that this is what caused the problem.
The specific problem that we try to address in this project is to magnify small signals, small motions, and complex realistic videos so that we can see hidden information that is very difficult to see with naked eyes.
The big challenge with this previous work is that it could only deal with videos where everything is mostly static.
There's a baby in a crib. Only the body or the baby is moving, nothing else. But if you go to a soccer game and you look at the player is moving, his leg is moving in a different way, his hands is moving, his head is moving. And if you put in multiple players at the same time, and for sure they're running at different speeds and different actions, put that in a bigger stadium where the fans are, you can imagine there are different types of motion at the same time.
If we try to amplify the big movements, they're going to overwhelm the small signal. They're going to hide the signal that's actually useful. So we need to be able to amplify the small things without being affected by the big things.
It's an algorithm or a computational analysis of the video. And so the video is a signal that varies with time, or composed of multiple signals that varies with time. So our algorithms will take these signals, separate them into different types of signals, then isolate some of them, magnify them, then make them back into videos so that you can visualize them.
We have this example of somebody firing a handgun, and there is a fair amount of movement of the arm because of the recoil and things like this.
And we would like to analyze how the muscles of the player are impacted by the gun shooting. So there is a reaction from the gun on the body or on the hand, and this impacts the muscle. Could lead to some injuries, could lead to some missing the target. We'd like to see what's happening on this part of the body, of the muscles.
Small movements happen everywhere, and in particular, small movement of the human body can be very relevant to medicine, of course.
So we are building a technology to help surgeons in laparoscopy to identify or figure out where the vessels are. They are hidden in the tissues of the body, and before cutting these tissues or seeing them by their eyes, we tell them where they are and mark these areas. We identify the vessels based on the blood pulsing, and we capture this signal and identify where it is, right, and try to mark it and color code it, so there is highly likely you'll find the vessel in this area.
So we're having some good initial success. The early results that we have are very encouraging. So actually, both for medicine and for sports, performance and speed are very important because you want the result right away.
We want to magnify things in real time while they're happening.
I would say we're halfway there. We can do the computation in real time for standard video resolution, and now the challenge is to take it to HD resolution and 4K resolution for future television, but we're almost there and we have good optimism.
Our colleagues at MIT are great. They're experts in these domains, and we complement each other. They come with graphics and signal processing background, and we come with experience in systems building and multimedia and video analysis.
And so it's really the combination of QCRI's expertise on sports application and our expertise in the analysis and visualization of motion that made this work possible.
So the whole work is quite exciting and interesting, and my team and our collaborators are all excited about it. And even when we show it to potential users, become very, very interested and then say, we hope to get that.
What's really exciting to me about this kind of work is that it's very visual. This is computer science that you can see. This is computer science that you can show. And really everybody can appreciate the results that we have because they really speak directly to our visual system. And when we succeed, it's not just new numbers, new data analysis, it's really new images. It's a new window over the world that allows us to see things we couldn't see before.
The problem is quite complex, quite challenging, but has lots of opportunities. And we're trying again to move it step by step to wider set of applications for this technology. And we see huge opportunities for this.